Integrals being the opposite of, we have talked about integrals being the opposite of differentiation. We have talked about area under the curve. We have talked about a lot of different things about integration, but we haven't done it with just equations yet. So this is what I want you to do. I want you to find a function for me whose derivative is 5x to the fourth. So let me just give you an example. So like, and I'm going to use a capital F of x for this. So I'm going to give you an example of something that doesn't work. So 10x to the fifth. Okay? If I have 10x to the fifth, if I take the derivative, then I would get 50x to the fourth. So that would be wrong. That would not be a function whose derivative is 5x to the fourth. So find me an equation of a function that has a derivative of 5x to the fourth. Everybody got it? What is it? It's just x to the fifth, all right? So, and I'm going to use a capital F, and capital F is what we typically use. Like, if we were taking the derivative of f, we would use f prime. If you're starting from a lowercase f, if you're wanting to integrate it, get back to the original function, then you would typically use a capital F to signify that that is the integral. So, x to the fifth. All right, is that the only equation that will work? Let's see. What about if I had f of x equals 5x to the fifth plus 3? What's the derivative of that? That is still 5x to the fourth, right? What about if I had f of x equals 5x minus 10? Still 5x to the fourth, right? And we could get crazy with some fractions, like having maybe some complex fractions that would work, but if we did, it would still simplify to be 5x to the fifth. So as far as the variable parts go, x to the fifth is the only thing that works. But if we could have any constant added on the end out here, because when you take the derivative of a constant, you get 0. All right. So the way that we write this, when we are taking, these are called infinite, it's called infinite integration. Whenever we take the integral of this, we are going to put x to the fifth plus capital C. And so when we integrate something, we can put that capital C there, and that tells me that I could have any constant added to this. I'm not sure what that constant is. And so a word I really have not used up until this point is antiderivative. I've been using the word integral, and integrals and antiderivatives are the same thing. But capital F of x is an antiderivative of f of x on an interval I if capital F prime of x equals f of x for all x in I. Basically, if you take the derivative of capital F and it gives you lowercase f, then you have an antiderivative there. So, I need to hold on. my notes because I wanted this blank to write it in. So I gotta make sure. So a little bit of notation. One of the ways we have shown a derivative is we have written dy over dx. And we would say that it equals, for right now, I'm just going to put some function f of x. So if we're saying the derivative equals some function that's f of x. Okay. If I want to solve this equation for y, then I don't need to have the x over here. I would just want to have the y. So I could multiply both sides by dx. And so that would give me dy equals f of x times dx. And so this sets up what we call a differential equation for us. It's a very simple differential equation. But the operation used to solve this equation for y is called anti-differentiation or indefinite integration. So far, whenever we have used that integral sign, we have had limits like from 3 to 7 of f of x dx, right? And that meant the area under the curve from 3 to 7. If we want to do a general integral or an indefinite integral, we just write the integral sign, and it does not have any limits on it. I really should write that down here. So we've got the integral dy equals the integral of f of x dx. And when you take the integral of dy, because that represents the derivative with respect to y, or the derivative of y, the integral of the derivative is just y. And over here, you would have the integral of f of x dx. So I'm just trying to show you a little bit of notation. And really, we've already been using this notation a lot, because you may have been wondering, as I was writing all those integrals, everything I did always had like a dt or a dx or something on the end. And it's kind of like we never really did anything with the dx or the dt, but it was always there. So the parts of this expression right here, this part right here, the f of x, the function, is called the integrand. And the integrand is what you're taking the integral of. It's whatever function you're taking the integral of. This part right here, the dx, that is my variable of integration. And so that dx has to be there on every problem. It is something really easy to forget and neglect to write down, because it doesn't really do a lot, because it's really just there to tell us what we're taking the integral of. It's kind of like when you do in your calculator. Let me show you. It's kind of like your comma x. So let me just pull up the calculator here. And so whenever you take this integral, we can say that it equals capital F of x. And then we'll have to have a plus c right here. And that c is called our constant of integration. So let me just give you sort of an example of why that dx has to be there. I'm going to give you just two problems. If I have the integral of k dx versus the integral of k dk. Alright, so if I have the integral of k times dx, what is the variable of integration here? It is x. So that means we treat any other variable like it's just a coefficient, like it's just a constant, right? So if I integrate this, what would have a derivative of just k? Kx. So this would be kx. All right, plus c. We put a plus c because you can have any constant added to the end right there. So k times x, if you take the derivative of k times x and you're treating k like it's just the constant, then you would have k as your derivative, so this would work. But if I have the integral of k dk, k is my variable of integration. So my k is actually the variable this time, not a constant. What could we do that would have what function could we use that would have a derivative of k where k is the variable? This one's harder. Like, for example, if I tried k squared, what's the derivative of k squared? 2k. Not it, right? What could we do to make that work so we just get k? We put 1/2 k, then we'd have 2 times 1/2, which would be 1, k to the first power. So 1/2 k squared plus c. Okay. So that's the difference there in why we have to have that. Most of the time, you're just going to see a dx there. We use dt a lot if it's a problem that has time in it, but that's why it is there. If you see other letters, but you have a dx, then those other letters are just a constant. If you have a variable and then the d matches it, then it's your variable there. All right, so I want you guys to try these. Okay, see what you can come up with that would have an integral of, or a derivative of 8. And then try these, do as many as you can. So let's look. What did you guys get for your capital F of x for number 1? 8x, and we're going to put a plus c on the end because there could be any constant there. Oh, sorry. I love that frozen feature, but I forget about it a lot of times. All right, so 8x plus c. That looks great. Okay. What about for number 2? Very good. Capital F of x would just equal c. Wonderful. All right. Any constant right there, you take the derivative of it, you'll get 0. Okay. What about for number 3? 5x squared plus 3x plus c. Very good. Okay. What about for number 4? X to the 4th minus 3x squared plus 2x plus c. Does that look good? Okay. What about number 5? Okay. Alright, before we do 6, I am going to write it like this. It's negative 2x to the negative 3 plus 3. That might help us a little bit there. What could we get for that one? What? Let's see. That would be, yes, because this would be x to the negative 2, and when you take the derivative of it, you get negative 2x to the negative 3. Right, so beautiful. Alright, so you may or may not have had time to get every single one of those, but I think you probably are already sort of formulating something, a short or a rule in your mind that you're using, right? What are you doing each time in order to come up, like for example, from 40x to the 4th, how do you get from to 8x to the 5th? Okay, you definitely add 1 to the exponent, right? And then how do you get from 40 to 8? Okay, whatever you could multiply by that exponent to get 40. Or we could think we could take 40 and divide it by that 5, and that would give us 8, right? So if we think about that, like right here, if I add 1 to the exponent, that gives me x to the 3rd, right? If I take 27 and divide it by 3, that gives me the 9 that I need here. So on the next slide there, we've got some rules. And they are directly related to differentiation rules we already know. So if we take the derivative of c, we get 0. Well, if we take the integral of 0, we get c, because they're inverses of each other, right? If we take the derivative of k times x, where k is some sort of constant here, we get k. If we take the integral of k dx, we get k times x plus c. So if this was a k here is a constant term. Right? This is a property that we've really already looked at. I normally do these notes before I do my properties of integrals notes. But with derivatives, if we want to take the derivative of f plus g, we can take the derivative of f and g separately. The same thing is true with integrals. We've already looked at this property. If I need to integrate f and g, then I can integrate those two separately. They're separated by plus sign. Okay? And so what we've kind of been coming up with here is the opposite of the power rule. The power rule, when we had x to the n power, to take the derivative, we multiplied out front by the n, and we subtracted 1 from the exponent. Right? Well, this is the opposite. We are going to, if we're integrating x to the n, we are going to add 1 to the n and divide by n plus 1 on the exponents. So that is your power rule. So whenever we have a problem, like we see here, that we need to solve, we're going to use that rule. Now, I am going to give you a couple of these. These are differential equations. There's really not much to this. It's just your book asks some of the questions like this. I wanted you to see it so it didn't throw you off. If the derivative dy over dx equals 5x, technically what you're supposed to do is you should multiply both sides by dx, which gives you dy equals 5x dx. And then to get rid of the d that's with that y, you would integrate both sides. Now, I don't really expect you to write that every time because it is just you're just integrating 5x is all you're doing there. But that's the notation that you're supposed to use. It is going to be more important when we get to our chapter on differential equations, but for right now you don't necessarily have to write that step. So we would get y equals, when we integrate 5x, we would raise the exponent 1, so that would give us x squared, and then we would divide out front by that 2. So we'd have 5 halves x squared, and we would always put a plus c on the end. Okay. And you can check these really easily just by making sure that the derivative does equal 5x. So if you multiply 5 halves by 2, you get 5. Subtract 1 from the exponent, that will give you 5x. Okay. So over here on example 8, you would multiply both sides by dx, and then you would integrate both sides. Don't necessarily have to write that step, but it is going to give you y equals. So your rule here, increase your exponent by 1, so 3 becomes 4. Divide out front by that 4. Of course, you could simplify that. I'm going to here in a minute. The next part, you would have x to the third. You would divide out front by 3. And the last part, you're just going to put an x with that, and then we always have to put a plus c on the end. Now, obviously, we wouldn't want these fractions that can be simplified, so we would write this as 2x to the fourth plus 3x to the third minus 4x plus c. Okay, questions here? The dangerous thing about this is it's as simple as using the power rule. The dangerous thing is now that I'm teaching you this, when I go ask you to find the derivative of something, you're going to get your rules mixed up. And when I ask you to take the derivative, you're going to actually integrate. Or if I ask you to integrate, you might take the derivative. So it's generally fairly easy to do, but you just have to make sure you're always using the right rule. Because if you're asked, like a question, like if I asked you to find the derivative of 3x squared plus 2x, everybody in the class would get that right if I asked you to do that for me yesterday. But if I asked you to do it today, some of you would say x to the third plus x squared because you would integrate instead of taking the derivative, and then you would be wrong. So you just got to be careful with keeping those, making sure that you're only integrating when you're supposed to integrate. But if we're going to do just a few more examples, this first example is pretty straightforward. You'd have 3x, and then you would have minus 5 halves x squared plus 7 thirds x to the third plus c. There. So just raising your exponent 1 and then dividing out front by that exponent. Okay. The next 3 are just a little bit trickier because you've got some fractions, so and some negative exponents. So this one, first of all, let's think of this not as the square root of x, but let's think of it as x to the 1/2 power. So if we're using that rule, we are going to add 1 to our exponent. So when we do 1/2 plus 1, we are going to get 3/2. And depending on how good you are with fractions here, you're going to divide by that exponent. If you're really good with fractions, then you know dividing fractions is easy as pie. You're going to flip the second, multiply. You can simplify this all in one step. If you are not so great at doing that part in your head, write it out the long way like this. 1/3/2 is just going to be 1 times 2/3. So you end up with 2/3 x to the 3/2 plus c. Okay. Questions? 11, this is the integral of x to the -4th dx. So we would increase the exponent 1, which is going to be -3. And then we divide out front by -3. So, and we'll have a plus c. This will probably be written as -1/3x to the 3rd plus c. It's easy to get the negative exponents mixed up because whenever you add one, it makes you think it should be 5, but it's really negative. Alright, now I have not taught you a quotient rule or anything like that for number 12. So this looks like a problem we cannot do, but we can do it. What could we do so that this would no longer be a fraction here? Good. So, well, we can do that. So we've got x to the -1/2. When we do that, we do still have to have x plus 5 in parentheses. Okay. And then if we've got x to the -1/2, we could distribute that because we don't know a product rule either. So we could not take the derivative like it, take the integral like it is. But we could distribute, and we would have, what are we going to get when we do x to the -1/2 times x to the 1st? X to the +1/2. And then we'll have plus 5x to the -1/2. Have not taken the integral yet. Okay. The other way to get there is to do love connection. You could do the love connection also. So you would have x plus 5 over x to the 1/2, and you could do the love connection there, and you'll get the same thing in that case. So to integrate this, x to the 1/2, that's going to be x to the 3/2 when we add 1. Then we have 1/3/2 out front, plus x to the -1/2. When we add 1, we get x to the +1/2. Then we'll have 5 over +1/2 out front, plus c. If you can do this part in your head, go ahead. That's wonderful. But I would rather you be slow than wrong. So if you need to, write that extra step there. So 1 divided by 3/2, dividing fractions easy as pie, flip the second and multiply. That's going to give you 2/3 x to the 3/2. And then right here, 5 divided by 1/2, that's 5 times 2 over 1. So that is going to give us 10 x to the 1/2 plus c. Okay, questions? Okay, your assignment, and we're not going to get to the other thing I was thinking about doing today. Your assignment is going to be on page 287. It's 1 through 22. So I'll just give you guys some time to work on that now. Also, don't forget, test corrections are due on Friday. So if you have any questions that you need to ask me about on those, you're welcome to ask me. I'll be here Thursday. I should be in here in the morning also, tomorrow and Thursday and Friday.